Good afternoon, SciPy 2020. I'm so glad to be with you again. This year, I think this is, 18th or 19th year. My name's Eric Jones. I'm CEO at InThought and have had the pleasure of being at all of these. I'm so sorry that we're not together this year in person, but we're together in spirit. And the conference has been amazing. Even in this new format. And one of the great things about that is so many more new people are able to join because of it. So welcome to everybody who is new. We're glad to have you. Today, the schedule first for me on announcements is to go through, first of all, thank yous. This conference, we got a bit of a curveball this year with COVID. But the team has really knocked it out of the park, and so even with all of the new technologies and new approach, they've really done a fantastic job, and we'd really like to say thank you to all of them. And there are a lot of people that are involved with this. First of all, I'd like to just say thank you to the organizing committee. We don't have time to go through everybody's name here, but I just want to leave this up for a few minutes for you to realize how many people are involved at the organization level in how many committees are involved and how many people are involved in making this happen, and how diverse, distributed of an effort this is across the SciPy community. So thank you to everybody on this list for the significant effort they put in to lead a committee and to make sure that everything went off successful this year. So thank you, virtual clap to the organizing committee. Really appreciate the work you've put in. Additionally, there are other committees for the tracks and mini symposia that are in charge of certain topics, such as the high performance computing or the machine learning, these different groups and community members have stepped up and also really organized these talks to make sure that the topics are great and that we have a good set of discussions around each of these. So thank you to all of you for taking the time to moderate these. Really appreciate it. And then finally, on the global things, we have a list here that actually goes along 3 pages. And these are the group of people involved in making SciPy happen, doing all of the big jobs, but that are behind the scenes to make all of this work. So I think the list has about 250 or 300 people on it. So thank you so much to the SciPy community for making this conference successful, to making it a community effort, and to keeping it as impressive and such a nice place for scientists to gather across so many different disciplines together. All right. And then finally, I want to make a special shout out to Jonathan Geyer and Corin Webster. They have been involved as the co-chairs this year. They probably didn't know what they were signing up for last year with the change with the COVID changes, but they've really managed it with aplomb and very appreciative of all the effort that they put in. So thank you, Jonathan. Thank you, Corin, for all the effort that you've done to make this a wonderful week for all of us. And then the last but certainly not least, I'd like to thank Jill Cowan and Kristen Leiser for their organization of the conference and making sure that everything ran smoothly. Anybody that is involved deeply in this conference knows how much work these people put in to make it successful, and really to make it where Jonathan and Corin can focus on the big issues that come up, and all of the details will be handled behind the scenes. And Jill has done this for, I believe, the last 5 years, has been the head of the SciPy conference. And it's bittersweet to announce that she will be retiring this year. So everybody that has ever had an interaction with Jill at the front desk or through email, you know what a pleasure it is. Jill, thank you so much for all of the time that you've spent on this conference, the labor of love that you've made it, and the quality and care that you put into that. So thank you very much. We're so glad that we've gotten to work with you on it. And we wish you the best in your retirement. You deserve it. And with that handoff, Kristen will be taking over. So I'd like to introduce Kristen as the new organizer of SciPy. She's had a wonderful teacher in Jill, and is incredibly capable, and we're looking forward to years to come of amazing conferences put on by Kristen. So everybody meet Kristen. Be sure to say hello, and please give her all the help she needs to make sure that next year is just as cool as this year is. All right. Next, the poster winners. So we had a poster session this year, and we have a couple of winning posters. The first one that I'd like to announce is Napari. I guess that's how you pronounce it, Napari. And the author list here reads a little bit like a United Nations subcommittee, but I'll try to do my best with names. We have Kira Evans, Tally Lambert, Kevin Yamauchi, Ahmet Kansalak, Shannon Axelrod, and this one's going to get me, but Lloyd Royer, Juan Nunez Iglesias, and Nicholas Sofranu. And so if you haven't looked at Napari, please check it out. This is an incredibly interesting tool dealing with large sets of data, making it very effective to quickly scan through and visualize this data. And a big deal on this is that word annotating. All of you that have dealt with deep learning know that all of the glory goes to, I guess, the GPUs and all the big compute, and all of the grunt work goes into labeling data sets. And this is really the hard part for scientists in specific domains. And so Napari is really a great tool and a pathway for us to have a generic tool that really helps across domains. So congratulations to these guys. Great poster. And then the second is Compile, and this is by Aditya Bhosale and Prabhu Ramachandran. And Compile is a tool for Python once, parallel computing anywhere. And anything that Prabhu is involved in, you probably have pretty pictures of grid-free CFD images that were developed through Compile. So please go check this out. It's a great talk. Thanks to both of them. Now on a bit of a different note here, but a wonderful topic. I'd like to announce that Emily Peace has her wedding this Sunday. And Emily is one of the committee chairs for our tutorial session. And Emily met her husband 2 years ago at SciPy. And Alex Chabot and Eric Michaud at InThought put together this cool sticker for their upcoming wedding. It's wonderful to see that SciPy goes further than just science and into the other very meaningful parts of our lives with relationships. So congratulations to Emily on her wedding, and thanks to the guys for putting together this cool tribute to that. I think the other relationship talk I remember seeing was Catherine Duff's talk, I think, about her wedding and doing her invitations through Python during one of the lightning talks. So it's not the first time, but this is certainly the first time that we've seen a relationship that we know about start and then have a wedding at the end of SciPy. All right, on to sprints. There is a separate event and crowdcast for sprints. Those start tomorrow. Please refer to the conference logistics and Slack if you need help getting in there. Everybody's welcome. This is not an experts only notion, far from it. We want everybody to come. If you're new to sprints, you'll be able to meet the leaders of projects, connect with them via Slack and Google Meet. There'll absolutely be an opportunity for you to contribute. And really, it's a great way to learn how to get involved in open source projects. So I definitely encourage you to attend. There are many different projects that you can get involved with, from scikits-image to NumPy. Nepari's on the list, many different ones. So check out the details in the Slack channel and sign up. And also you can email scipy@inthought.com for an invite. And also, finally, before we get to keynotes, I'd really like to thank our sprint sponsor this year. And they're somewhat shy, so we can't show their logo, but everybody is familiar with NIST. And we really appreciate NIST stepping up to the plate, as they do most years, to provide funding and support for SciPy. And this year they sponsored the sprint. So thank you so much. We really appreciate it. All right, the schedule for the day: we have the keynote, then we'll have a Q&A session. We have a material science Q&A at 4, and then breakout rooms and networking at 5. So I hope you stick around after the keynote. And with that, I'd like to introduce our keynote for the year. I think perhaps, I guess maybe people aren't aware, but there's a large team of people that have been working on this very impressive project called the Event Horizon Telescope for a decade or more, perhaps. And here's a picture from 2016 of the entire team. And I think certainly the scientific community might have been aware of what they were doing, and certainly astronomers were. But beyond that, they labored sort of in the background for many years. That all changed on April 10th, 2019, when the first image of a black hole event horizon was made available to the public. And this is a huge kind of holy cow experience to see. I can remember actually first seeing it. And it was very similar to the year before, I believe, when we first got to hear about and see gravity waves. And so these are the images and the experiences that really make you proud to be a human and part of science. It's amazing what we can do when we put our efforts together like this. And I would love to say that my introduction to this came through a very important scientific journal, but with a number of my news sources, or mine came through Reddit. And this was the image that I got. And this is an incredible image inside of an incredible image. We get a lot of things in this picture. We see the excitement of a scientist that gets to experience a discovery from this huge collaboration with the Event Horizon Telescope. It's kind of first light of this. And then you see down in the corner, you sort of see the image that she's looking at. But so as a member of the SciPy community, I often look at different things, and I'm looking at things in between those two levels. And what I noticed was, is that matplotlib? And incredibly, it is very cool. And of course, we see that Python is used in many different places, but this gives us another level of pride to see what our community gets to be a part of. And immediately we started talking about how would we get somebody from this effort to come and talk with us, because we get to live vicariously through this. We build the tools as a group, and I know that John Hunter is smiling down on this from above to see that his tools are used in such an incredible way. But that's the tip of the iceberg. NumPy and SciPy and many other tools are used inside of here. So we know that our community had something to play in this, and it's wonderful to be able to bring a team member from EHT to be able to talk with us. And so with that, I'd like to introduce Andrew Chael. And Andrew is a member of the team. He graduated from his undergrad at Carleton University, which is a liberal arts institute up in Minnesota, I think around 2013, and started his PhD at Harvard in astrophysics around 2014, and really got drawn in at that point into the Event Horizon Telescope project. Prior to that, I'm always curious about the journey that people take. And Andrew started with an interest in astronomy, partially because his parents were both scientists, geophysicists at Sandia National Labs. They had telescopes, and really at a young age got him interested in that. But he went into college not sure if he wanted to do science or whether he wanted to do history. And in fact, he got a concentration in medieval studies while he was at Carleton. So it's really a diverse background. And I love to see scientists that have this diversity, and also some of us in this community knew what we wanted to do really young. It's fun to see people that decide a little later along the process. But he did a project on pulsars his sophomore year and really got hooked from that to really focused on astrophysics. And so we're here now to get to listen to Andrew talk about EHT, the incredible image that we saw, black holes, simulation of black holes, and the future of EHT. So with that, Andrew, I'd like to turn it over to you.
Yeah, so thank you again so much for having me. This has been really a wonderful conference, and thank you for the organizers putting it together with all the additional stress of transitioning to digital. I know that has been a lot, and I think it's gone just incredibly so far. I've learned a lot that I hope to take with me and improve my code and my science going forward. So yeah, I'm here today to talk to you about this work that we did with the eht Collaboration, which is a global collaboration representing over 300 scientists around the world. And so I'm really speaking on behalf of this group. We have members in countries from Europe to the US to Asia to Africa. And so I just couldn't, this work is not my work in by any means. For the most part, it's the work of this incredibly talented and large group. And the thing I sort of want you to take away from this talk is sort of the process by which the eht made this image, but also just the idea that the eht is sort of a fusion telescope, and that we're combining antennas from around the world. We're combining lots of different software, from software that was written in the 70s. It's very hard and very few people understand how to use it, to software that we're cobbling together using all the amazing tools developed in this community in Python. And it's all joined together into one effort and to produce a computational telescope. And to produce the image that you all saw released last year. We're working on follow-up images to that, of course, like many efforts that has been slowed recently, but there will be more exciting science to come from the eht. And all of this science comes from this collection of different people around the world, from different antennas, and from all this different software, many different backgrounds, and from people really building on the expertise and materials that have been put together by communities like this one. So I'll start off by just talking about what the eht set out to see. What does a black hole look like? So if a black hole is, of course, this object that is so dense that even light cannot escape from it. So we might think that it's just inherently dark and there's no way to see it. But if you sort of trace the orbits that photons would take around the black hole, you see here in this image that a lot of light close to the black hole will be bent very strongly by the black hole, and some of it will fall in. If you're a light beam and you're traveling close to the black hole, too close, within this sort of critical radius, you'll fall in. And so you can imagine that if you have light just sort of bouncing around the black hole, light that travels too far will fall in, and light that is a little bit further away from that will be strongly deflected, and you can sort of try to back project this and make an image about what you would see if you were an observer far away, what the imprint of this black hole would be on the light around it. And this calculation was first done for the simplest kind of black hole really soon after black holes were discovered in the 1910s, and it's been a subject of interest ever since. And the basic feature that you would see is this shadow, which in the simplest case has a diameter of 2 times the square root of 27 times the sort of characteristic radius of the black hole. Its mass times Newton's constant over c squared. And so if a black hole is illuminated by light, it should have this shadow feature. And if we know from astronomy that black holes throughout the universe are definitely huge sources of energy and illumination. So black hole, if you think about it as this dark object, but really in the astronomical sense, black holes are incredibly bright. And this is because as material falls onto a black hole, it releases an incredible amount of energy. The black hole is so dense that the gravitational energy released from an object falling in from a large distance away right to the surface or the event horizon of the black hole can be up to a half of the sort of rest mass, its EMC squared. In contrast, for nuclear fusion, which we think of as this incredibly efficient process, the amount of energy released per unit mass is less than 1%. So this is an incredibly efficient process, and it lights up black holes in the centers of galaxies that we can see across the universe. So we call these active galactic nuclei. Here's an example of one that actually on cosmic scale isn't too galactic, but it's too active, but it's very pretty. And you can see sort of this light at the center of this galaxy. And at cosmological distances, with a lot of these nuclei, these black holes, which are engines powered by infalling material, releasing huge amounts of light, actually the light released by just the black hole can outshine all the stars in the host galaxy. So we know these black holes are huge engines in the centers of galaxies, and one of the other things that they produce, in addition to light, is jets of material. So the black hole that we imaged last year sits at the center of this galaxy M87, which is a giant galaxy not too far away, cosmologically speaking, and it emits this huge jet of material, which people have traced sort of more and more in toward the center of the galaxy over the last few decades. So we have this image of the large scale structure at thousands of light years of this jet coming from this galaxy, reaching these huge lobes of material. We can trace it in with finer and finer observations using the same technique that the eht used, just at larger scales. And we see this jet going into the center of the galaxy, sort of at less than light year scales here. And then finally, the eht has now revealed the center of this jet, the launch point, has this characteristic black hole shadow shape. I think we're seeing the structure very close to the event horizon of the black hole itself. And the structure that we see, we can model, and I don't have too much time to talk about this. This is a hugely important part of this process. We can model the structure that we see by simulations of light trajectories in the space-time. So we trace light rays back, and they're bent through the curved space-time as they get really close to the black hole. They pick up light through this emitting material. In this case, it's this sort of schematic. It's a accretion disk. And this accretion disk is shining light, and so we pick up light along these rays. We sort of backpropagate that to see what the black hole will look like. And we see this characteristic shadow feature surrounded by all this complicated astrophysical gas, which is determined, whose trajectories are determined by complicated computer simulations. But at its center, it still has this characteristic shadow feature of the same size that was first worked out almost 100 years ago, or more than 100 years ago, I guess. So the size of the shadow on the sky is very big in one sense, because we're looking at a black hole which is huge. We're looking at a black hole with several billion solar masses in size. So it's in one sense, very large. It's a shadow that's bigger than the solar system. But at the distance of this galaxy M87, 50 million light years away, this shadow becomes incredibly small. So the size that we're looking for, this characteristic size across the shadow diameter, is 40 micro arc seconds across, or maybe more familiar units, that's 10 to the minus 8 degrees. And to give you a sense of how small that is, this is 1 pixel on the Hubble Space Telescope, and we're now zooming in from that 1 pixel to the size of the eht image. So it's many, many times smaller than even 1 pixel on one of our most powerful telescopes. And I got this animation from Twitter from Alex Parker. I really liked it. It popped up the day that the image came out. Another way to think about this, the size of this image and what a challenge this represents, is that the black hole shadow is about the same size to us as an orange on the moon. So if you were to place an orange on the surface of the moon, it would subtend the same angular distance that the black hole subtends to us. This is a very sharp picture of the moon taken by one of the strongest ground-based telescopes. You can see a lot of topographical detail in this picture, but even in this picture, every pixel is 1.5 million oranges across. So this is a very difficult challenge to image something this small from the surface of the Earth. And in fact, if you just work out sort of the resolution limit that we need to achieve this, you discover that we need a telescope at the wavelength we're operating at, which is 1 millimeter. We're looking at light that is 1 millimeter wavelength. We need a telescope that's about the size of the Earth. And NSF funds us very nicely, but they don't fund us quite that much. So we have to find a way around this this problem of the size of the telescope that we need. And the way to think about the technique that the eht uses, called Very Long Baseline Interferometry, is that instead of like a normal telescope, which works by collecting light rays from the source across the surface of a mirror and combining them at a focus, we're basically collecting light rays from the source all at different telescopes around the Earth, and then combining them coherently in the same way that a large dish would in a computer. So this is the sort of the sense in which the eht is a computational telescope. And
Andrew?
yeah.
I'm so very sorry to interrupt. There's been a few comments in the chat that people are having a bit of trouble seeing your screen.
Oh no.
Do you have the ability to make it a little larger?
Oh, is it not full size? Sorry.
That's great. Thank you.
I thought it would be full size. Okay. Sorry about that. Okay. So yeah. So that's the basic idea behind the eht. And now I will sort of get into a little bit more of the details and the process and the software behind the image that we released last year. The SMA and JCMT on Mauna Kea in Hawaii, the Large Millimeter Telescope in Mexico, APEX and ALMA telescopes in Chile, and then the South Pole Telescope at the South Pole. These are very lovely pictures of all of them. But then we also have this computational eht, which I alluded to before. So once these telescopes get the data and they're combined in correlators, we have to do an incredible amount of post-processing on this data to extract the image structure from it. And this uses many, many tools. Since I'm at a Python themed conference, I am highlighting the Python tools here, but there are many other software packages and software languages that go into it. But really, the work that I do, which is focused more on the image reconstruction and image analysis, is really driven by Python and all these Python tools that people have put together over the years, and just would really be impossible without all the work that everyone in this community does to put these two together. So thank you again. How does the eht work? So Very Long Baseline Interferometry works by combining signals coherently from telescopes separated by large distances. So if we have two telescopes here in South America and here in Europe, we can take the signals from those two telescopes and correlate them. And at the end of the day, what we get between those two telescopes observing at the same time is a single measurement of the Fourier transform of the image. So one measurement of a spatial frequency in this Fourier plane, representing one Fourier amplitude component. Of course, if we could cover the Earth with telescopes, we would have a filled-in Fourier transform. We'd be able to we'd have all this data on the Fourier transform of the image, and we'd just be able to invert that directly to get our image. But really what we have is a sparse collection of telescopes carving out very narrow tracks in this Fourier space. And we get more information as the Earth rotates, because the size of these baselines changes as the Earth rotates, projected as seen from the source. But still, at the end of the day, with our very small number of stations and just one rotation of the Earth, we get a very limited amount of measurements in this Fourier plane. So we have to invert this limited amount of data we have, this sparse data set, into an image. So in 2017, we observed the source at these sites around the world, and here are some of the teams that did this incredible work of observing. You know, a lot of astronomy these days is been really streamlined in a way that you can just observe from home. It's automated in a way that you don't have to go to these sites, but really for the sites, the work that we're doing, it's still, you know, very cutting edge in the sense that we're using new backend devices. We're really pushing these telescopes to the limit. So we have to have people there, and people who are really expert in outfitting these sites go and do this work every year that we observe, and it's incredible to see it all come together at the end. I, on the other hand, was not able to go to these sites, so I stayed here in Cambridge, Massachusetts, and sort of watched it unfold at this, what we called central command, but we were really just observing the observers. And a great tool that we actually developed using, the people in Europe actually developed for this software tool is this VLBI monitor, which allows us to compare the weather at all these different sites. And this, I think, was put together in Python and is this incredible tool that allows us to instantly sort of get a diagnostic readout of all the sites, because we need the weather to be good everywhere in order to have a good observation. And that can be a challenging task to compile all these forecasts. This monitor tool really helps with that. Once these people at the site start the observations, they sort of turn on these advanced back-end systems, which have been built specifically for the eht. So these are sites that, you know, weren't built directly for the eht. The telescope itself was built for some other purpose. It's funded and developed by some other agency, but we come in and that makes it quite difficult to sort of unify all of the data from these very heterogeneous telescopes. We come in and people have, in collaboration, have spent a long time developing these sophisticated back-end systems which plug into the telescope and collect our data, digitize it, and record it to hard disk. And so these are incredible works of engineering that people have worked on for over a decade now. And they're able to record data from the telescope and write it to disk at about 8 gigabytes per second. And so at the end of the day, we have petabytes and petabytes of data on these special disks. And we're sampling the signal and down converting it just to 2 bits, but at such a rate that it fills up these petabytes of disks relatively quickly. So here's a picture of Katie at the end of the day with the sort of initial haul of disks right after the observations. So the way that works is now that once we have the data recorded to disk, we ship all of these disks to a central facility called the correlator. This is still the fastest way to transfer this data, is just to ship it directly, because there's so much of it. We play it back and correlate the signals between each pair of telescopes to create these Fourier amplitudes and phases that we need to reconstruct the image. Then we have to go through this complicated and difficult and time-consuming process of calibrating the data to sort of remove all of the instrumental effects from the telescope, to remove particularly the effects of the Earth's atmosphere, which are a real problem for us. Find the weak signals and enhance them before we can then move on to reconstructing an image and trying to find our best image from these data. And so sort of the data path that we have throughout this process is that we're recording petabytes and petabytes of information, but most of this information that we record directly from the telescope is noise, either from the atmosphere or from the telescope system itself. We correlate it down, reduce its volume by a lot, and then calibrate it and even further to extract the small amount of physical information about the source structure that's hiding in this mountain of data. And then the final image that we end up with, as you can probably see by now, it's still pretty blurry. We're not reconstructing the details of the source because our resolution is only so fine, but our final image only represents a few kilobytes of information. So it's really this incredible path, taking all this huge amount of data down to the small amount of physics we can extract from it. I'll just say one or two things about the data calibration step, which is really one of the most critical steps in this whole process. And extracting an image and interpreting the physics of it would be impossible without this really painstaking work of calibration. So one of the things that we're doing in the calibration step, and this image is taken from Lindy Blackburn, who led the calibration effort, is removing the effects of the Earth's atmosphere. The Earth's atmosphere is bouncing around on timescales which are really fast compared to the the timescale of the source we're looking at. And you can see this sort of on the left here, these phases between different telescopes are really rapidly moving around. And so this means that like interpreting this data and averaging it down to enhance the signal to noise is really impossible if we just look at the raw data. So calibration attempts to model the atmosphere and remove this stochastic pattern and sort of lock it on to the information about the source, removing the atmospheric turbulence from the equation. So you can see sort of at the end of this calibration process, we have nice stable phases and nice stable data that we can average for long time scales and really get a great picture of the source. And this whole process, sort of on a software side, is really driven by sort of a combination of really old code first developed in the 70s, some of the 90s, C code for VLBI systems, sort of interfaced with Python and plotting, SciPy and pandas and matplotlib libraries to really make it accessible and pipeline all this data through it. So this has been an incredible work by the calibration team to process all this data and to validate it. And I'll just say a word about the validation step as well. This has been critical, led by Maciek Bulgas, to look at all of the data, to verify that all the quantities that we expect to be distributed normally are, to compare across different frequencies, different polarizations, and different data reduction pipelines as well, to make sure that we don't have any systematics hiding in our data. And so this is also this sort of validation library and pipeline that Maciek put together is also built in with pandas and SciPy sort of at the core, and is critical for really trusting our data. Okay, so once we have this calibrated data, it's gone through this painstaking checking to make sure that it's robust, that it's removed the effects of the atmosphere as much as possible. We still have the problem that we have only a sparse collection of measurements. So we can't directly invert these data using a Fourier transform to get an image. We need to pass them through some kind of imaging algorithm to get a reconstruction. And because we have a sparse collection of measurements, the source structure is essentially unconstrained. There are sort of an infinite number of images which can fit our data. And those infinite number of images will have different properties. Some of them might be very noise-like. Some of them might look nicely like a black hole. Some of them might have lots of weird side lobe patterns. And so we need to apply additional information to our sparse measurements to pick out what we think is the most likely measurement, what the most likely images. And in addition to the fact that our images are sparse, we also have the fact that though we have attempted to remove much of the atmospheric turbulence, we're unable to remove its effect entirely. And so we have to account for that in the imaging process as well. The way that we did this, this imaging process was sort of in two different frameworks, one of which is sort of in the standard in this field in very long baseline interferometry for decades now, which is this inverse modeling approach where we attempt to we just take a Fourier transform of the image and attempt to clean it up. Basically, this algorithm is called clean. We try to remove the effects of all of the missing information in the image domain. So we use this technique and software for this technique, which has been around for a long time. And we also combined it with sort of newer approaches, which were developed extensively in the collaboration, and one of which I worked on as a big part of my thesis, which instead of trying to remove the sort of corruption and the noise from the image, we sort of attempt to model it and find an image which maximizes a sort of a posterior probability, or something we can think of as a posterior probability. So we have a likelihood that our image, any given image, will match the data. We can incorporate all of the different sources of noise and systematic error that we know about into this likelihood. And then we also have a prior probability that the image is a good fit. So for example, a noise-like image should be really disfavored by a prior. An image which is too extended or covers too much area in the sky when we know that the image is compact should be disfavored. There are lots of different, these priors are what we call regularizing functions that go into this process. And a lot of the effort is in sort of choosing these best regularizers and finding the right combination of weights to get a good image. So we used both of these different approaches because we wanted to make sure that our imaging processes were really robust and that we were able to recover an image of the source using both well-established methods and newer methods. They both have different strengths and weaknesses, but at the end of the day, we wanted something that to present to the community, to the world, that was really robust to the choice of method. But on the sort of maximum likelihood side of the imaging, we developed 2 new software packages for the eht, both of which you can use for all sorts of problems in astronomy and radio interferometry and optical interferometry as well. So one is eht-imaging, which I helped develop. Going into this whole process, I knew very little about software development. I was an astronomer. I didn't really know how to write software for anyone other than myself. And so this has been an incredible learning opportunity, helped by all the people across the collaboration, but then also, again, by all the code in SciPy and NumPy and all these other libraries that we're able to leverage and build on to build these libraries. There's also the Smiley image reconstruction package, which was led by Kazuo Akiyama, who is currently at MIT Haystack Observatory, but is also affiliated with National Observatory of Japan. And so both of these packages were developed, like I said, for the eht, but have many other applications. So here's an example of a different source imaged by the ALMA interferometer in Chile of this disk, this protoplanetary disk around the star HL Tau. You can see on the left sort of the image that was first produced by Clean using the traditional techniques in interferometry. On the right is an image that we created with eht-imaging. And so you can see actually eht-imaging removes some of these features around here, which might be imaging artifacts that Clean has a difficult time with. So that's all to say that this software is driven by the eht, but has a lot of applicability for the rest of the community as well. So the eht imaging software library, like I said, was a huge collaborative process to put together. It would have been impossible without the Python community, without the SciPy community. And it's been really gratifying to see everyone in the collaboration and more people in the community start to use it as a framework for developing new tools. Like I said, I didn't go into this intending to build a software that would be used by other people as sort of a standard package, but now that that's happened, I sort of really see the fun and the just satisfaction you get out of building something useful for other people and working with other people to help that tool become more useful for them. But at the core of eht-imaging, also I want to say, sort of at the core of what we're doing when we're imaging is we're minimizing an energy function, and that SciPy powers the very core of our code. The main imaging methods we use are powered by SciPy minimize, so it's right there at the very core. And it went through the image that you see, the image that was published last year, sort of went through these SciPy functions in order to come out. Okay. Once we've run our data through all these different imaging algorithms, and we have all these different images, how do we verify that what we're reconstructing is real? How do we have absolute confidence that we're presenting this first black hole image, that we're really showing an image of structure that we think is real? Like I said, there's an infinite number of images. This data we have do not uniquely determine the image that we reproduce. So we need to have a lot of confidence that our methods are producing something sensible in order to have confidence presenting it and interpreting it scientifically. So we went through this sort of verification process in 2 steps. One step was with blind imaging. So this was basically, we divided ourselves up into 4 teams. And these different teams approached the problem with, we got the data in, I believe, in June 2018. We got the data. We were not allowed to communicate with each other for 7 weeks. And we worked on these, the imaging independently in these 4 teams using different tools in isolation for 4 weeks, so that by the end of the process, we would present our best guess image using our different methods, and if they agreed, we would be happy. If they disagreed, we'd have to really go back to the drawing board and think, what can we even really say anything about these data? Do we really understand it at all? So after working diligently in secret for 7 weeks, we came together and revealed our images for the first time. And this is what we got. And you can see, these images are different than the final image that was produced, we went through a lot more verification and fine-tuning of our algorithms before we produced a final image, but they still all show the essential features of the image that was published, which is this ring of a characteristic size of 40 microarcseconds on the sky, which is brighter in the south, has this enhanced brightness down here. And this ring feature really is the signature of this black hole shadow, and so we were all really excited to see this. I was personally expecting it to be a lot harder and a lot more difficult to interpret than this. So it was just a really gratifying moment and definitely the highlight of my last few years. Here we all are on the day that this image came out, and just was so happy to actually see this work coming to fruition after such a long time. Once we had these first images, we then went through a more systematic second step to validate our imaging methods and to sort of test different hyperparameters in our imaging codes to make sure that we weren't fine-tuning or locking on to an image that was what we wanted to see. We wanted to make sure that we weren't choosing the settings in our code in order to produce an image that we expected to see. And so we did this by using a library of synthetic data built on several different source models of different shapes and sizes, and we ran these synthetic data through the same imaging pipelines with all these different combinations, 30,000 sets of hyperparameters, and we demanded that the hyperparameters that we chose as sort of the fiducial hyperparameters were able to distinguish between all these sources. So if the source had been a filled disk instead of a ring, we would be able to tell with our imaging method. If it had been a double source or a collection of blobs, we would be able to tell. And then we applied these same parameters to the actual data to get our final image, which remained a ring. So this ring structure and the brightness enhanced in the south is robust to the choices we made, and we are confident that if we had a different structure, we would have been able to reproduce that accurately. So at the end of the day, we produced images on 3 different imaging pipelines using 3 different software libraries: the eht-imaging library that I wrote, the Smiley library that I talked about before, GIFmap, which is a sort of a workhorse tool of astronomy using the clean method, and we produced images on all of these different pipelines on 4 days. So we see the structure is consistent from day to day, which is another big source of relief that we're not seeing something that was only there on one day. It's persistent and independent observations from day to day. And then we, to get our final image, we've blurred these images to an equivalent resolution and averaged them so that we're really only focusing in on the features that are common to all 3 imaging pipelines, and it's maximally conservative in terms of what we interpret at the end of the day. This is the final image we produced. It was the sort of source of the end result of many years of work, and definitely and a huge amount of work, not only by our collaboration, but as I said, by the whole Python community and other software communities went into producing this image. Okay, so in the last bit of this talk, I'll say briefly what this image tells us. What can we learn from this image? I won't have enough time to go into this in as much detail as I would like, but it gives us a flavor of what we have learned from this image already, and at the very end, what we will hope to learn in the future. One of the sort of first level things that we learned from this image is the mass of the black hole in M87. The size of this ring feature is proportional to the mass directly. And previous measurements, which had attempted to sort of determine the mass by looking at the influence of the black hole on stars and gas around it, disagreed. And so one measurement gave 3.5 billion solar masses, and one gave 6 billion solar masses. So we were able to distinguish between these 2 scenarios, these 2 prior measurements, to get a 6 billion solar mass, to get a final mass that was closer to the 6 billion solar mass measurement. And the way that we did this was by modeling the image that we got with rings of different diameters and different features. And we did this modeling with the nested sampling technique, as well as other MCMC methods. But I'm highlighting this nested sampling technique, first of all, because I have this really nice animation, all produced in Python and matplotlib, done by Don Pesci, sort of showing the exploration of this space and how we're locking on to different parameters like the diameter of the black hole, but also to highlight this was done in this Dynasty package, which is a pure Python package that implements nested sampling. It was developed in astronomy by by a fellow grad student for completely different applications in the EHT, but we were able to use it use this open source software to make this critical contribution. And so I just think that's another great example of the way that the Python software community has helped this project. So at the end of the day, we got a diameter measurement and a mass measurement from that technique, as well as from several other techniques, and they all agree on a mass of the black hole of 6.5 times 10 to the 9, 6.5 billion solar masses, which agrees with the previous stellar dynamical mass measurement, but not with this other measurement. And just to put that in perspective, this image came out the day after we released the image to the world from XKCD, which was really exciting and gratifying to see. The sort of putting this image into context with the solar system. The size of the ring of light that we are seeing is bigger than in diameter than the radius and the current position of Voyager 1 in our solar system. So this is an absolutely massive black hole, but it's just really far away, and so it is really small. Another way to put this in perspective is this is sort of an image of black holes that we've observed with gravitational waves, which exist in this other sort of population of black holes, of stellar mass black holes, of masses that are around 10 to 20 to 40 solar masses. These are what we see in gravitational waves. But if we were to put the eht in black hole on here, the M87 black hole, first of all, we'd have to go to a log scale. Otherwise, our black hole would be a mile across. But this is what we get, something that's tens of millions of times bigger than those stellar mass black holes that we see in gravitational waves. So I'll say briefly about something about the M87's physical environment and what we interpret about the gas falling into the black hole. So we know that there's a thick accretion disk of hot plasma that's lit up to billions of degrees Kelvin, which is producing the light that we see. We think that accretion disk is powered by strong and turbulent magnetic fields to launch this huge jet that we saw in these images I showed at the beginning of the talk. We can simulate this process, and this is sort of the other half of my research that I won't have time to talk about in detail, but we simulate these processes with supercomputer codes that solve the equations of the coupled fluid or gas and magnetic field in the curved spacetime around the black hole. And so we evolve these disks of material which develop turbulence and power huge jets and outflows, and then we ray trace light rays through this material to sort of simulate movies of what the emission will do over time scale. So we see in this movie that has come from a simulation, we see that there's a lot of gas that's turbulent and it's swirling around and doing complicated gas things, but then there's the central image of the black hole that's imprinted on the space-time, which is that same radius that we're observing with the eht. And so to interpret the image completely, we sort of have to incorporate both the effects of the geometry of the space-time as well as all the turbulence of the astrophysics. So that's been a huge effort as well. It's still ongoing. We've put together many different simulations run by different groups. Each of these individual simulations can take weeks. From these simulations, we've developed a huge library of images which we can compare to our data and extract physical information about the source from. This is just showing sort of what a simulated image from one of my simulations looks like. If you had infinite resolution eyes on the sky, you would see this central ring with all this turbulent stuff around it. And if we put it through the same imaging pipeline that we subjected the real EHT data to, you get this, which it doesn't look exactly like the EHT image because we're looking at just one snapshot, but looks very similar, and we would interpret the same physical things from it that we do from the real image. Okay, so at the very end here, I'll just mention some of the next steps we're doing now, what we can expect to see from the EHT in the coming year. One thing that we're looking at right now that I've been really involved in is the polarization structure. So light has an intensity, but it also has a direction. We've observed this with the EHT, and this direction of these little vectors and these two simulated models here show the direction of polarization on the sky. And this, it turns out, traces magnetic fields in the image. So we can interpret the polarization image, which we'll be releasing soon, in terms of the magnetic fields and use it to learn something about what the magnetic fields are doing near the event horizon of the black hole and how they're powering the central engine and these jets that we see emerging outside of the galaxy. Another source we're looking at is the black hole inside of our own galaxy. This black hole is much smaller than the black hole in M87. It evolves much more quickly. It is sort of whipping around on timescales less than a day. So taking an image of it is much harder. The analogy that we like to use for this is that M87 is like you're taking a picture of someone who's sitting still and posing for a camera. Sagittarius star is like taking a picture of a dog that's like running across your field of view as you're trying to take the picture. It's moving really quickly underneath us, and so it's more difficult, but we're making great progress on that and hope to have a final result from that soon as well. And then lastly, going forward, the EHT, has been this incredible effort over a decade to put together this network of telescopes and develop the techniques and tools that we need to interpret their data and process them into an image. But we're just getting started in the sense that we're hoping over the next years and decades to add more telescopes to this array, to build it up. And one of the things that we hope to do with that is to really get a sense not only of the structure near the event horizon, but also how this sits in a larger context. So how does this structure near the event horizon power this larger jet? If we can develop more sensitivity by adding in more telescopes and sort of filling in our information with new telescopes around the world, we can really start to see not only this shadow feature which we imaged, but also how it sits in its environment, how it launches this huge jet to large scales, and then also how it evolves over time. How is this gas orbiting and falling in, and what can that tell us about the processes that are operating right here near the event horizon? So that's the end of my talk. Thank you so much again for inviting me. Just in summary, I'd say again, the EHT image that you saw last year was really the result of a huge collaboration from people working on the instrumentation side, building telescopes, building backends and telescopes, traveling around the world to observe, to people like me sitting more on the interpretation side, developing algorithms and techniques to produce images and to interpret them physically. And all this wouldn't have been impossible without the ability to rely on software like SciPy and all the other Python tools that we use in our analysis. So thank you again for having me, and I'm happy to take any questions now.
Great. Incredible talk, Andrew. Thank you very much for that. So we'll open the floor for questions. There is an Ask a Question button down on the bottom right-hand side of your screen. And so if you'll put something in there, then we can follow up with asking those over to Andrew. There's one question here from Karen West. Have you determined why one side of the ring is brighter than the other?
Yeah, that's a really great question. So the reason that one side of the ring is brighter than the other is basically because we're not viewing this black hole face on. It's sort of at a slight angle to us. Mm-hmm. The material that's orbiting around it is coming toward us on one side and receding from us on the other side. And the material that comes toward us is boosted. It's moving at speed near the speed of light. So light from that material is sort of enhanced, and light that is emitted by material moving away from us is sort of enhanced and diminished. And so that's the contrast that we see. If we had been viewing the black hole sort of more edge on, it would have been even more extreme. We're only viewing it at like a 20-degree angle. So it's just a small effect, but we could expect in different sources to see a much more extreme contrast.
So there are a couple of questions here about the weather and also about coherence time for the atmosphere. So one of the general questions is, how often is the weather good enough everywhere to make an observation? And then what determines the coherence time for the atmosphere? How does it depend on wavelength?
Yeah, so the coherence time for the atmosphere depends really sensitively on wavelength, in that we're sort of pushing it at 1 millimeter. At lower frequencies, it's much slower, and so you can, it's much easier to deal with. At 1 millimeter, the atmosphere is moving around very quickly. And it's also really only possible to do these observations at 1 millimeter at very high altitude at very dry sites. So that's why all of our sites are, we have sites in the desert in Chile, in the desert in Mexico, and top of a mountain in Spain, and at the South Pole, which are all very dry places. And so you really need to get to the very high and dry places for this to work. And even then, the weather is really only good a few months in the year. In 2017, we had incredible luck at getting wonderful weather everywhere for our week of observations, which was incredibly lucky. In 2018, we observed again, and the weather wasn't so good at a lot of places. And so, we're expecting that data will not be as, we added some sites, so there will be great things to learn from that data as well. But there are other things that will be less good about that data. So there's actually a paper, I think, which will be coming out relatively soon about looking more systematically at the weather, the impacts of the weather in sites, and how we can sort of use weather information to pick optimal locations for new sites. It's a paper that was been led by a grad student and postdoc in my old group. And so it's a question we're really interested in. It's a really difficult one to sort of pick the optimal times for observing and optimal sites given the weather.
Great, thanks. The mundane stuff, right? The mundane stuff gets in the way. And that turns out to be 95% of the work much of the time, or maybe 99.5 odd things. Here's another one that there are a number of upvotes for. This is very, I guess, focused on the software side. But can you discuss the tools from the SciPy ecosystem that the EHT is planning on to rely on in the future work? I would guess some of the ones that you've mentioned are kind of staples. Are there particular ones that you wish had enhancements, or that really may play a role in the future, or anything like that?
That's a really good question. I think I found that the SciPy ecosystem is so rich that a lot of the things that we think about what we want, and then it's wonder if it's there in SciPy, and it turns out to be. So I haven't really encountered anything yet that I really wanted to be in SciPy that hasn't been. If I do, I'll definitely let you guys know. One thing that we're looking at now for the first time in some projects is to understand if machine learning and deep learning can play a role in the eht. Astronomers have lots of different opinions about how much we should move towards trusting these machine learning techniques, but for the simulation side, it would be really helpful, for example, if we could generate simulated images using a model trained on existing simulations and get new realizations of the turbulence in our images, for example, that are physically real, for physically reasonable, without having to run a huge supercomputer simulation. So that's sort of a direction we're looking forward to moving in, which might use a lot of the techniques that people listening have helped develop.
Great, thanks. And I guess some of what you just mentioned kind of feeds into this next one. I guess we wouldn't be in 2020 if there wasn't a question about neural networks, right? So have you considered physics-informed neural networks as a means of processing your sparse data? It seems like you're confident in your governing equations given results from your simulations.
Yeah, so specifically for physics-informed neural networks, I don't know much about them. I know that they're sort of recently emerging as a big thing, and I would definitely like to learn more, because I think that is the central concern that astronomers and physicists have about just sort of blindly dumping our data into a neural network. Is that what if it's violating simple physics? So that would, I think, be a great direction. We've used some neural network imaging algorithms, and they produce the same sort of image structure as the very simple gradient descent ones that we used for the initial results. We've used some neural networks in a preliminary way to, like I said, produce more simulated images, with more realizations of the turbulence. I think this is definitely an area we're going to keep exploring in, and hopefully there'll be some results for the next few years coming out of that exploration.
Well, I appreciate that the questioner asked, and considered physics-informed neural networks, because it means we're making progress on people's understanding of things that we, in this field, we really can't leave the physics behind.
Yeah.
On doing things. Well, Andrew, I believe that's all time we had for questions. Thank you so much. Are there any parting comments you'd like to make?
No, I just thank you so much again for having me, and stay tuned. I'm hoping we'll have some great new results from the eht coming out soon.
Well, thank you. I've just been watching the comments scroll by, and a lot of appreciation for the work that you're doing, the team's doing, and thanks so much for sharing with us.
Thank you again.
All right, Jill, with that, I'll turn it back over to you.